Hello everybody, today I'm going to be talking about translation initiation for both prokaryotics and eukaryotics, as well as regulation of translation for both prokaryotics and eukaryotics. Mostly I think focusing on eukaryotics just because there's a lot more stuff, but I would say the process is very similar for both, but eukaryotics of course have a more complex system for translation initiation. I am not going to be talking about elongation and termination just because they're both relatively similar and there's a lot more videos on YouTube that do talk about it. I'm just, to be honest with you, the initiation stuff is a lot more in-depth and I do want to cover that just because I think it's important. But other than that, let's get started. As always, I have a game plan. I say that every video, and it should be on this side of the screen right over here, and that's gonna be what I'm talking about today if you needed more confirmation. There's also going to be sRNAs and riboswitches. That's the translation regulation for prokaryotics. I just didn't put it there for eukaryotes, for prokaryotes, just because I had forgotten before I started writing the game plan, went over my notes, and then I put it back in. So I am going to be talking about riboswitches, sRNAs. I know siRNAs are there as well. I'm going to be talking about both sRNA and siRNAs. So yeah, let's get into it. So we're going to start off with prokaryotic initiation, and for both eukaryotic and prokaryotic initiation, the first step is you do need to charge up your initiator tRNA. And so for this example, I have the MET tRNA. It's the MET tRNA FMET, as in MET for methionine. That's the amino group that's attached to the initiator tRNA. So I'm just pointing that out there. This reaction requires ATP. So you're going to use a molecule of ATP. The enzyme that does this reaction is transformylase. You're basically just adding a formal group, or I guess in this case it looks like an aldehyde, and you're adding it to the amino group. And so before this step, I have mentioned that methionine is added to the tRNA by an aminoacyl tRNA synthetase. That just adds that methionine or just the amino group in general to the initiator tRNA. But as I said before, the formal group is going to be added to the amino group, creating an N-formal methionine, and that's going to be your initiator tRNA. That's what activates your tRNA, so that's how we can put it in our P site. Otherwise, it's not going to work. So now that we have our charged tRNA or charged initiator tRNA, what we're going to need to do is we need to have the ribosome load onto the mRNA, and to do that, it comes out in parts. So the prokaryotic ribosome consists of the 30S subunit and the 50S subunit to create a 70S subunit. It's not like an addition, like as in like there's no simple like arithmetic. There's no 50 plus 30 equals 80. It's 50 plus 30 equals 70. That's just how they have broken down when centrifuged. But anyway, we are going to be using the smaller component of the ribosome, the 30S subunit. That has three slots, an A site, a P site, and an E site. The A site is the aminoacyl site, the P site is the peptidyl site, and then the E is the exit site. So when you do your initiator tRNA, when it binds to the 30S subunit, it's going to bind to the P site. And this is why, because the initiator factors 1 and 3, those ones will bind to sites A and E respectively. So initiation factor 1, or IF1, is going to bind to the A site, the aminoacyl site, which means that the initiator tRNA is forced to bind to either P or E. The next initiation factor to bind is initiation factor 3, that's going to bind to the E site, which means that when tRNA binds to the ribosome, it only has one slot to go in. It's the most favorable site, which is the P site. So now that we have our open P slot open, we have the mRNA. So it's going to bind to, let me just rephrase that. The 30S subunit is going to bind to the mRNA, and within the 30S subunit, there is a section or like a little compartment known as 16S rRNA, which is complementary to the mRNA shine-dalgarno sequence, okay? So the shine-dalgarno sequence is a sequence right before the start codon, so it's basically like a guide before the start codon. So the ribosome or the 30S subunit is able to bind correctly and identify the right start codon. Start codons are always AUG. For the shine-dalgarno sequence, it's typically AGG, AGG. I think there's a U there as well. Don't quote me on that one. But that is the shine-dalgarno sequence. It's basically like a sequence before the start codon that designates where the ribosome is, like, it basically delegates if the ribosome is going to bind to the correct start codon. So at this point, we have formed our pre-initiation complex. So yeah, we've made it this far. And now at this point, we just have to bind our initiator tRNA to the ribosome, or I guess our 30S subunit still, and then we have to assemble the full ribosome with the 50S subunit to make 70S. So in order to do that, we need to bind initiation factor 2, which is a GTPase, okay? So it's bound to GTP, which means this could be a hint to that it could be hydrolyzed, so some sort of dissociation will go on. But at this point, initiation factor 2, which is a GTPase, will bind with initiation factor 1 in the A site, and the initiator tRNA, its only option is to go to P site because everything else is blocked. So it's going to go into the peptidyl site, okay? Another thing that happens here is the anticodons will pair up with the start codon. So the start codon, like I said before, is AUG. The anticodon will pair with the G, so it's going to go from CAU. So the codon will be read AUG, the anticodon will be read, I believe it's UAC, because the codon 1 will be anticodon 3, and so on, right? It's 3, 2, 1, the codon is 1, 2, 3. Okay, so the last step here is we need to form the 70S initiation complex, and to do that, we need to get rid of our initiation factors in order to put the mushroom cap on. And by mushroom cap, I'm talking about 50S because it looks like a mushroom cap to me the way I've drawn it. So I'm going to refer to it as a mushroom cap, but I'm going to try my best to go for the 50S because I'm getting confused looking at this and I'm thinking that it's a mushroom. But anyways, so there's a conformational change because of the fact that we've added our tRNA, initiator tRNA, and it's bound to the start codon with its anticodons, right? It's basically, it's base paired, right? This is a conformational change within the 30S. So initiation factor 3 will dissociate. And at the same time, initiation factor 2, its GTP will be hydrolyzed to GDP plus phosphate, or a phosphoryl group. And so because of this, the other initiation factor 1, can leave, which also causes the association of 50S. So IF3, or the initiation factor 3, when it leaves, it basically says, hey, let's come to this party or something like that, to 50S, and 50S is like, sure, why not? 50S joins the party, but nobody's there because everybody left, but it's happy with 30S. So now you have 50S plus 30S, and the initiator tRNA makes that 70S initiation complex. I just want to make a side note because I know I'm not talking about elongation, but I want to make this brief so you can kind of understand how everything moves in the same direction, because the ribosome is reading, it's going from 5' to 3', and so when the tRNAs come in, when they're shifting out, they're moving to the other side. They're moving towards 5', but the ribosome is going from 5 to 3. The tRNAs are shifting from 3 to 5, okay? And so how it works is you have the A site and the E site unoccupied. The P site is occupied by the initiator tRNA. So it's the first tRNA. You're always going to have methionine. What happens is the A site is empty. You need a charged tRNA, and that's what I talked about previously, is you need that formal group because you cannot put it in without charging. What's the point, right? You cannot start an electric car without putting electricity into it, putting energy into it, right? So your charged electric car, let's say your Tesla, is going into the parking spot or whatever, but you have your initiator tRNA, you have the next charged tRNA, let's say it's an alanine, And so what's going to happen is they're basically going to go like, basically that's what's going to happen. They're forming a peptide bond between the methionine and the alanine. Okay, this does not require ATP because we've already gotten the energy from charging up the tRNA that came into the A site. And then now that they're together, they have that peptide bond, it's going to transfer everything over to the A site, and then they're going to shift from 3' to 5'. So it's going to slowly go from, this is A site, this is P site, now this is in the P site, now this is in the E site, it's going to leave, and then now this tRNA has the methionine and the alanine attached. So another tRNA is going to come in, it's got glycine, they're going to kiss again, they're going to say, this kiss didn't really work out, we're not really good, we're not good together. It's going to transfer over the peptide, or I guess, yeah, the peptide at this point, move over, bye-bye. And that's it, and that's how you're going to be doing, you're going to elongating this. The anticodon is going to be reading the codon. You know, that's how it works, is like you get the tRNA that matches with what you have written down, right? And then that's how it works. So that's a side note on elongation. I didn't want to make it I did want to be super brief because I don't want to go into like a whole tangent about it, but yeah, that's pretty much the rundown on elongation. So now that we have gone into initiation and a little bit of elongation for prokaryotes, now we're going to go into regulation of that for prokaryotes because of the fact that we can use different methods to inhibit or activate translation, such as using a molecule called sRNA, which is pretty much small bacterial regulatory RNAs. I don't know, the names are goofy, so don't ask me about that. But basically, what you want to have happen is you want to activate or inhibit translation by targeting the RBS, or the ribosome binding site. The ribosome binding site does contain the shine-dalgarno sequence within it, so I feel like that gives you a hint because what I said earlier, shine-dalgarno sequence basically guides the ribosome to the correct start codon. So, in order to activate it, basically in this scenario, a hairpin will have binded or have bound itself to the RBS. And to unbind the RBS from the hairpin, all you need to do is you need to take this sRNA, bind it, its complementary base pairing to the hairpin, which will kick off the hairpin. What's going to happen is the hairpin is going to dissociate and the RBS is free to bind with the ribosome, and that will activate translation. To repress it, sRNAs can just bind to the RBS, which is unobstructed, and that will not allow any ribosome to dock because it cannot bind to the RBS if an sRNA is blocking it. And that's pretty much how you can activate and repress translation using sRNA. Another thing to regulate prokaryotic translation is to use something called riboswitches, which is basically when a metabolite binds to an aptamer, which sequesters the shine-dalgarno sequence within the hairpin stem, which means that the ribosome cannot bind to the correct start codon because it doesn't have that guide sequence as in that shine-dalgarno sequence. Basically, that's pretty much how you can use riboswitches to inhibit translation. Moving on into eukaryotic translation initiation, instead of the ribosome being 30 and 50, it's going to be 40 and 60. So the smaller subunit is going to be 40S, and the bigger subunit, or I guess the taller subunit, is going to be 60S. You still have your A, P, and E sites, but for the eukaryotic translation initiation, it's a little bit more complex, but it still has the exact same concept as prokaryotic translation initiation. So the first step is you're going to have initiation factors 1, 1A, and 3 will bind to the 40S subunit. So the E in initiation factor 1, 1A, and 3 are just meant to categorize that as the eukaryotic initiation factor. But initiation factor 1A will bind to site A, and initiation factor 1 will just bind to site E, so that leaves slot P open for the initiator tRNA to bind. Initiation factors, both of them, 1 and 1A, are both homologs. So yeah. The initiation factor 3 will bind to 40S to prevent premature subunit joining, or like the whole complex association, because 40S is not meant to bind with 60S right away. It's after everything has been assembled. 60S will then bind to 40S to make 80S. So the next step is you have your initiation tRNA or initiator tRNA and another initiation factor will form a complex. So the initiation factor forming a complex with the met tRNA is going to be initiation factor 2, which is a GTPase. That will bind to the P site of the 40S ribosome. And the other initiation factor 5 and 5b will also associate with the initiator tRNA and the initiation factor 1a. 5 is not shown on this diagram, but 5b is a GTPase. This whole thing that associates with the ribosome will form a 43S pre-initiation complex. So once you have formed the 43S pre-initiation complex, this complex will then bind to an mRNA, and this mRNA is mediated by initiation factor 4F. This reaction does require a molecule of ATP to be used, and after you have bonded with this mRNA with this complex, you get an even bigger complex called the 48S particle. So taking a closer look at initiation factor 4F, this is the multi-subunit complex that mediates that mRNA. So in this complex, you have initiation factor 4G, which is the adapter protein. It is the scaffolding protein that holds onto this whole complex. You can see it attached to the initiation factor 4E, which is the cap binding protein. So it will hold on to, or it will bind to the 5' cap of the mRNA. The initiation factor 4G is also attached to initiation factor 4,3, which I did mention at the start of the translation initiation. That is the protein that's basically like, no, 60S, you can't get in here. Not yet. You're not needed here yet. You also see that 40S is attached to the initiation factor 3 because of the fact that it does bind to 40S at the beginning. Initiation factor 4A is also bound to initiation factor 4G. 4A basically has helicase activity, so it does unwind any hairpins that come when the 48S particle scans. Another thing that is attached to 4G that is not in this diagram is PAB1P or PAB1P. It is a poly A binding protein. So moving back to the 48S particle, what the particle will now do is it will scan the mRNA from 5' to 3' while holding the 5' end of the mRNA. So initiation factor 4E from the initiation factor 4F4 complex will basically hold on to that 5' end and will pull the mRNA, so the whole complex will just kind of mediate this pulling. The complexes in the 4F4 will be holding and pulling the mRNA from 5' to 3', scanning for something called the Kodak sequence. The Kodak sequence is essentially what is specific to eukaryotics to what the shine-dalgarno sequence is to prokaryotics. So it is a sequence that delegates which start codon is the most favorable and the most correct one to start translation. And so the Kodak sequence is pretty much a purine residue, so adenine or guanine, which is 3 residues before the start codon, and immediately right after the start codon will be a guanine residue. So this is kind of what the scanning looks like as I'm demonstrating here. But I also switch ways to kind of demonstrate, but also keep in mind that the 5' cap is being held onto as the mRNA is being scanned. So once the 48S particle has located the correct start codon, which is of course, our AUG that is universal for both eukaryotes and prokaryotes, the anticodon can complementary base pair with the start codon as the AUG, and now the 60S subunit can now bind to the 40S subunit. But to do that, like in the prokaryotic translation initiation, what needs to occur is the initiation factors have to dissociate from the 48S particle in order for the 60S to join the 80S, or to join the 40S to create an 80S initiation complex. So how does this work essentially? Basically, in this case, to dissociate all the initiation factor 5, which is, I know, not pictured on this diagram, stimulates the hydrolysis of initiation factor 2's GTPase. So the GTP that is bound to initiation factor 2 will be triggered to dissociate, but it's not technically hydrolyzed at this stage yet. But initiation factor 5 does stimulate the hydrolysis of initiation factor 2, which lessens the affinity for initiation factor 2 to the tRNA, the initiator tRNA. And what this does is, because it is lessening the affinity to the tRNA, initiation factor 5b will then hydrolyze the GTP for initiation factor 2, which does release it from the initiator tRNA, and all the other initiation factors here. So initiation factor 1, 1A, 3, 5, 5b, all of those, and N2 do come off, which do allow the association of 60S onto the 40S subunit with the initiation tRNA still on there to create the 80S initiation complex. Two kinds of ways that you can regulate translation for eukaryotes. Of course, there are many more, but these are the two main big ones that I want to talk about, is the MTOR pathway and the reversible phosphorylation of initiation factor 2. So for mTOR, basically, in this case, you have this inhibitor of translation called 4E-BP1. And so to activate translation, you need to phosphorylate 4E-BP1. And so this is done through mTOR. You will have some sort of stimulant that will approach a receptor, bind to the receptor, and these receptors are RTKs, or receptor tyrosine kinases. They will auto-transphosphorylate themselves, which does trigger a signal cascade, and through there the mTOR pathway is activated. mTOR will then phosphorylate 4E-BP1 because mTOR is a kinase protein. And so 4E-BP1 is then able to dissociate itself from initiation factor 4E. And if you remember initiation factor 4E, that is the cap binding protein to the mRNA. So when the 48S particle is scanning, it'll hold onto the 5' end, and then it will just kind of like drag everything, all of the mRNA, until it finds the Kodak sequence. So when the 4E-BP1 protein, the 4E-BP1 is not phosphorylated, it does inhibit translation because it does not allow that 4F4 complex to form properly, which does not mediate the mRNA scanning for the Kodak sequence. So the ribosome is not able to find the correct start codons because of the fact that this complex is not properly built or properly associated with each other. Okay, so let's talk about the regulation of initiation factor 2. And so if you can recall, initiation factor 2 is super important because without dissociating initiation factor 2, you cannot add the 60S subunit for the ribosome, which means you can't even form the 80S initiation complex. That's the first big reason. Second is you won't be able to find the right start codon because it forms a complex with initiator tRNA, as in initiation factor 2. So those are the big two main reasons that stand out to me. And initiation factor 2 has 3 binding sites. It has alpha, beta, and gamma. The alpha site for sure is the phosphorylation site. So when you do phosphorylate this protein, what happens is the second, or the homolog, actually the homolog is initiation factor 5, but there is another initiation factor called 2B, which will then exchange the GDP for GTP for initiation factor 2. And if it is phosphorylated, the 2, the initiation factor 2B will be sequestered to initiation factor 2, which means it cannot bind to 40S ribosomal subunit. So basically the ribosome is screwed. So you can't even do translation because initiation factor is basically like, I gotta go, I'm busy. So yeah, those are the regulation pathways or regulation methods for eukaryotes.